So might as well get going. I think it might be a shortish class today because of the material we have to cover. I usually say that, then it doesn't work out to be, so don't get your hopes up too much. If there's a chance to talk, I'll probably talk for the duration. We talked about plate tectonics being a useful construct for us in trying to understand exactly how heat fluxes around the globe were distributed. We note that they're concentrated at plate boundaries because that's where the crust is thinnest and the underlying magma highest in elevation within the section, and therefore at the shallowest depth. We note that the other thing that relates to those plate boundaries is that not only is heat flux highest and the location of the molten rock highest elevated in the section, they're also host to most of the hydrothermal deposits around the world. And that is because in those regions where you get active deformation occurring, either by either by the subducting slab going down here, or deformation that occurs ancillary to that, or the deformation that occurs at constructive plate boundaries, there's enough deformation that's going on that it keeps fractures open, and therefore fluid transmission in those fractures is high in the solid earth crust, this thin veneer of 30 to 70 kilometers that exists on top of the molten subsurface. And that since heat is the since water is the agent by which we can bring heat out, then that's an important component, because we made the case that the heat rates that we have out of the system is a function of volumetric flow rate, density, and specific heat capacity, and the change in temperature as you go down depth. So having rock hot at shallow depths makes it accessible, but if you're not able to get volumetric flow of liquid through it, the heat transfer agent, water usually in our case, if you can't get this to be high also, then that's all for naught, because all of the terms in this equation have to be relatively large for the product of them to be large. Having one that's zero doesn't help you. So we talked a bit about the constraints on heat flow and how it's distributed, and in the US or in North America. And so today we'll talk about the agents by which heat is transferred by conduction and convection. And so relatively straightforward if it's within the Earth's solid crust. The crust is not moving, and so the only way that heat can transfer if fluid isn't carrying it is by conduction. And in the regions where convection currents exist below the crust, free convection of the molten rock occurs. So we need to talk a little bit about those two modes of transport. If we're talking about heat conduction, that follows Fourier's law. This is the heat flow which is in watts per meter squared, joules per Newton meters per second, or joules per second per meter squared. And this is temperature. This is the depth below the surface. And so if you go down from the surface where the temperature is 0 or 10 degrees, whatever it is at the surface, and down at the geothermal gradient to get to some temperature, then the mechanism by which heat is conducted to the surface is just by Fourier's law. This is the thermal conductivity. So, and thermal conductivity is in watts per meter per degree centigrade in terms of units. And so if you work out the individual components of this, you'd recover that because Just writing out the units of this equation: watts per meter degrees Kelvin, which is this, temperature, and meters gives you watts per meter squared. These both cancel out. So the negative sign is because the heat flow is in the opposite direction of this gradient, just by convention. Heat flow is not just a scalar property, but it has a direction. It's a vectoral quantity. So that's the negative has to be in there for that, but it's not too important other than that. And so below the solid crust, you can get convection because the actual rock there is molten, has a viscosity attached to it. And so the mechanism by which convection occurs is by physically moving the molten rock up as it becomes more buoyant. So as you heat it from some depth, we'll look at some relationships in this. Horrible notes, I realize. Some depth, then the geothermal gradient will supply heat to this at a higher temperature than the surface. As a result of that, any small packet of material will, as it's heated, will expand. By definition, if it expands, it becomes less dense slightly because it's occupying a larger volume, and density is mass per unit volume. The volume's changed while the mass is the same, the density is reduced, and as a result of that, you'll get convection occurring. So I guess this is starting, it's not necessarily any particular direction. If this goes up, this will go up to the surface here. Actually, I won't do that. I'll do the opposite. I will stick with this one, and I'll change the directions of these arrows. Because this, so you'd expect that unlike in conduction, there's a thermal gradient that goes from high temperature to low temperature. It's linear on it's a uniform heat transfer through a large flat plate, which is essentially what the crust is. And so there's a geothermal gradient there, which we've talked about being 25 to 50 degrees centigrade. If you look at convection, convection is a much more efficient way of transferring heat because it takes the temperature at this particular high temperature here and it merely translates it up here, not by being conducted, but by physically advecting it up to the surface. And so if you look at the profile of temperature as you go up on the limb of a convection cell, you'd expect the temperature not to change as you go up. If it was being conducted purely and it wasn't mobile, then it would be a linear temperature change. This is just constant. So it gets to the top at this temperature without changing very much. It will change slightly because it will cool as it rises. And as it gets here, the other stuff below is also wanting to come up, so it can't accumulate here, so it has to go to the right or the left. And so it'll choose one of those and it will set up a convection cell. And as a result of that, as it goes across this cold surface here, it will lose heat. It'll lose heat by radiation out of this, and so it'll get to this point where it's cooler, might not get back down to the temperature of the surface, and then as a result, if it gets cooler, it shrinks, it becomes denser again, and it goes down. And so the manifestation of going up, going across, and then going down is set up as a convection cell. And I guess I did, I think they have some examples of this here. So, just like a saucepan. I think they have so this is the idea. So you'd set up these cells below the crust. They end up self-organizing in some way. They would typically be roughly equiaxed. So if the height that it has to go through is controlled, then the width of the cells is also roughly the same as that. It would self-organize in that way. And you can imagine these being all kinds of weird, wonderful patterns. I don't know whether, I thought there was another one at the bottom which was, I go past, yeah, like this. So you can imagine these being folding over into each other and having adjacent areas that repeat. So just a very efficient way of getting a heated bottom boundary, reducing the density of the liquid, the fluid that's in here, having it rise to the surface, has to be a liquid, not a gas, then cooling and then descending as well. So that's the mechanism by which free convection occurs. And of course, free convection is what's happening everywhere where the crust is not solid. We can get convection in the crust, but it has to be convection of water being carried within fractures. And we'll talk about that. So if we're talking about Fourier's law, that heat transport per meter squared per unit area is equal to thermal conductivity and the temperature gradient. Then typical values of thermal conductivity are given in these two figures. I guess this comes from Glassey's book. It's just a plot of this figure, actually. So the rough magnitudes for solid materials, so this would be crustal rocks, which are made of quartz or calcite, carbon, etc., is something in the range of 1 to 5 watts per meter degree centigrade. And water down here is about 0.5. Important for us because it's going to be the heat transfer fluid that we use. And some of these conductivities change slightly with temperature, as you can see. The description of Fourier's law is just this, that the heat flux is related to conductivity times the gradient. I guess we already did check the units of this. If you take the units for thermal conductivity, you take the units for temperature, and you take the units for length of which it occurs, then Kelvin drop out and it becomes energy per unit area. So this is a simple way that we can do it. Actually, we already did use it. We actually have enough information here to use it in a useful way, in that, oops, didn't want to do that. If this was our crust, thermal crust, and this is the temperature that we have that's defining that behavior, temperature gradient, dt dx. If this is dt dz, I guess, if you want. We know the magnitudes of that, so we can immediately write exactly what we expect the heat flux to be, of the order of, it was 5 watts per meter degrees centigrade. We know that the heat flux is of the order of 25 degrees centigrade per kilometer. So if you multiply this by 25 times 10 to the minus 3 degrees C per meter, the minus 3 is just the conversion to get from kilometers to meters, then we end up with 125 watts per meter squared. No. Watts per meter squared. And so that is a milliwatt. And if you go back to looking at, so 125 milliwatts, perhaps you can't can you see that well enough? These are heat flow maps. This upper end of this is 150 milliwatts per meter squared. This is 15 to 20 milliwatts per meter squared. And so in regions where even the depending on the material, I guess. So we used a high-end value of thermal conductivity. If we use a low-end value, which was 1, so 1 watt per meter squared would give us 25 milliwatts, and 5 gives us 125. So that covers this whole distribution. So you'd expect, I suppose, that if we're talking about a thermal gradient which is relatively small, that we'd get magnitudes of this to be relatively small magnitudes of heat flux, representative of the part of the US or the continental North America that has low thermal gradients in it. Gradients which are in the range of, I guess, 40 to 60 milliwatts per meter squared. So anyway. So, if we want to be able to calculate heat flux, not just in this very simple geometry, where we automatically satisfy a conservation equation, energy conservation equation, we need to substitute Fourier's law into a conservation equation. So this conservation equation merely says, if you've seen this before, that if you take a cubic volume and you flow heat into this in the x direction, which would be defined by Darcy's law, the heat coming out of the other side doesn't have to be the same, because you also have potential that it could be coming out from the top or the other sides of it. If it's going through the system, it could come out through here, but it could also come out in the y direction or in the z direction. And the statement of conservation, that the energy that you put in here has to come out of the system either on one of these faces, is merely that d dx plus d dy plus d dz multiplied by the flux in each of those directions has to equal 0. So this is conservation of energy. It's saying that any energy that goes in here, it can't accumulate it because we're not allowing it to. Any energy that goes into here has to come out. It may come out from this face, but it can also come out of the other faces. And the mathematical statement of that is this. And if this, so this is just for one-dimensional conduction. If, for instance, the amount coming out for one-dimensional conduction was not the same on the other side as going in, then it would be a net accumulation. And the net accumulation would do something by increasing the temperature of this in a given amount of time for this flux that comes in. And it increases the temperature relative to the density of the fluid that comes in and its specific heat capacity. And so this is the conservation equation, diffusion equation, I guess, actually, for one-dimensional transport. So if you substitute Fourier's law into here and rearrange it, you end up with the diffusion equation. And this just says that the thermal conductivity, which has come from this relation here, times the second order derivative of temperature with space, with x, y, and z, has to equal the amount of heat that accumulates. And so if there's no heat accumulating, this term would be 0, and in 3 dimensions, this equation here, this would be replaced by, this would just be a second order PDE. So this would be d2t dx squared plus d2t dy squared plus d2t dz squared equals actually this rho c dt, change in temperature with time. So this would be the 3-dimensional version of this equation. So the coefficients we need to know something about are density, specific heat capacity, and thermal conductivity. We already talked about conductivity being in these ranges for different materials. If you look at thermal conductivity for water, I guess these are the same numbers we looked at. If you look at the density of water is 1,000 kilograms per cubic meter. Rock typically is 2,700 kilograms per cubic meter. It doesn't change very much. And specific heat capacities can be defined either at constant pressure or at constant volume. They don't change by very much. It just means that if it's at constant, we usually work with them at constant pressure. If it's a constant volume, you have to make a small adjustment there, but there's a very small change in them. So typical magnitudes of specific heat capacity are for water. Sea water is, we talked about last time, is it's 4,138 joules per kilogram per degree centigrade. And I think specific heat capacity for rock is of the order of 1,000 joules per kilogram per degree C. And I guess this 4.3 is that it takes 1 calorie to raise the temperature of 1 gram of water by 1 degree centigrade. And so I guess 1 calorie equals 4.138 joules. And a joule is a Newton meter. So the congruence between mechanical energy, I guess, and thermal energy is given through this. Calories are the same calories that you burn when you're exercising or walking around campus, and there's a commonality between those two. So I guess that these are written down here. So it's 1,000 joules per kilogram per Kelvin, and this is 4,187. I guess it wasn't quite right, but close enough. So the other useful number is to know thermal diffusivity. So if you take this equation and you divide both sides through by the density and specific heat capacity, then this term becomes 1, and you don't have to worry about it. And instead of thermal conductivity being controlling the behavior, thermal diffusivity controls it. So we'll define this. It's written here, but uppercase K is thermal diffusivity. Equals thermal conductivity divided by specific heat capacity and density. And that's a useful number. One of my colleagues told me this 30 years ago, and I still remember it, is that roughly for rocks, a good number for thermal diffusivity of rocks is, he said it this way, 10 pi meters squared per year. Strange units. So in other words, it's about 30 meters squared per year. So I'm thinking that if you took our values that we have, so we had what? We had 5, let's call it 1 watt per meter per degree centigrade divided by 1,000 joules per kilogram per Kelvin times 1,000 kilograms per meter cubed. I guess we know that a watt is a Newton meter per second. A watt is a joule per second. And so if you did the math for that, I won't do it now, but hopefully it would work out to be something of the order of this. So a good number to remember, useful. So that talks about, is perhaps an introduction to be able to talk about heat transfer. So the most efficient method of moving heat is by convection. We talked about the method by which that occurs in magma, by the fact that we have, at depth, we have a higher temperature and a lower temperature at lower elevation, and that the buoyant forces will drive it. It turns out that the parameter that controls that is called the Rayleigh number. And like all good non-dimensional numbers, it has no dimensions, but it's typically the ratio of two forces that are acting. And so the Rayleigh number is the ratio between the buoyant force of a packet of magma, which is sitting at the bottom, which makes it want to rise. As it expands, the more it expands, the lower the density will be. If it's sitting in a sea of higher density material and this has lower density, just like a cork held at the bottom of a swimming pool, it will try and rise to the surface. And acting against that is the viscosity of the fluid that it has to go through. So in moving up through this column, if you think of this little packet, it has a buoyant force that's acting upwards, and it has a viscous force that's acting down on it, on the sides. And so the viscous force is resisting it going up and going up. And so this is defined in terms of these parameters. So making it more buoyant is the thermal expansion coefficient. So the thermal expansion coefficient for rocks is typically something like 10 to the minus 5 meters cubed per meters cubed. So volume per unit volume. So it expands by 10 to the minus 5. So I guess that's 10 to the minus 3. So 100th of a thousandth per degree centigrade. I guess it's degrees centigrade. So volume per unit temperature. So this is in units of 1 over temperature. This is in temperature. So this is the difference in temperature between the base of the convection cell and the top, delta T. This is planet Earth, gravity, acceleration, the density of the rock. So this is density. And this is the depth. So this is the height of the convection cell. And as I said before, roughly these will develop so that they're more or less equiaxed. So it'll set up its own, by moving, it will set up its own pattern. That pattern can switch with time, but roughly they'll be equiaxed, defined by this geometry. This is the viscosity of the fluid. So for magmas, I guess what's the viscosity? Viscosity of water is roughly 10 to the minus 3 Pascal seconds. Air would be 10 to the minus 5, but this is magma, so this is probably 10 to the minus 10. I don't know what the numbers would be. Oh, I guess they're right here. These magnitudes. 10 to the minus, it would be high. 10 to the plus 19 in this particular case, if you can see that. So these magnitudes are, so this would be what's sitting right underneath the plates at 1,000 degrees centigrade. And so this would be what's acting, actually if this was the crust here, then this would be 1,000 degrees centigrade. And the lower mantle at the base would be 3,500. Actually these are, so they're in they're in degrees centigrade. So they're only off by 273 if you move between degrees Kelvin. And so yeah. And what's viscosity? Yeah, okay. So for free convection to occur, you need this number to be bigger than about 1,000 for it to set up these cells, and you can check whether that is the case for that. And this is, yeah, what is K? I forget what K is. Thermal diffusivity that I just defined, right? So this is the same expression here we're using. So yes, this is thermal diffusivity. which is in units of length squared per time, meters squared per second. So that's for the behavior in the below the crust. If you look at what's happening in the crust, which is solid, then you can still get convection occurring, but in that particular case, the convection cell would look exactly the same as before. It would be heating up this container, which has some height to it, which has a temperature on the top and a temperature on the bottom, which are different. But now the convection cell that's in here is flowing within a porous medium. And so the only thing that's flowing in that convection cell would be the water, which is able to go between the grains of the porous medium. And so the way that this is defined is in terms of fluid flow in a porous medium, and that is through Darcy's law. And that says that the velocity of flow is equal to minus the permeability divided by the viscosity and multiplied by the pressure change as a function of location. And so this term here is the permeability. And we should know that the units of permeability are in length squared. And so roughly the permeability of a medium is approximately equal to the pore diameter squared. So I'm not sure what I'm going to use. So if you think about this porous medium as being a whole collection of grains, and that the spacing, the pore space that is isolated by those grains has some diameter d, then the permeability is approximately equal to d squared. Has to be units of length squared. Can derive it, but we won't derive it. And so, in other words, this permeability takes the place of what it doesn't exist here in resisting the buoyant convection. So it tries to rise. It'll try to rise against a viscous force that's acting on the sides of it. In this particular case, the viscous force is the other static fluid with this little cube of fluid then moving up against relative to it. In this particular case, the viscosity of the system is manifest by the fact that the fluid is trying to flow up through here and it's rubbing against the static porous medium which it's going against. And so since we can define the permeability as proportional, actually equal to, not proportional, same units as, but equal to the grain diameter squared, we can actually end up replacing one of these length scale here just by the fact that this d squared term that exists here, d cubed term here, that includes the length dimension, splits up as being two parts. One is it takes a portion of the diameter of the pore space squared, because that's proportional to permeability. So we can write this particular portion of this relationship here, this and this. So all I'm doing is taking those components out here, replacing this d cubed term with d and d squared. And the d squared is proportional permeability. So the bottom line is that now the Rayleigh number, which is controlling whether it will convect or not, is again controlled by the ratio of the forces promoting buoyancy and the forces resisting buoyancy through viscosity, but now it's proportional to this behavior. This is again the thermal diffusivity, viscosity of water, so this would be the viscosity of water. If water is the fluid that's going through it, we just said that that is roughly 10 to the minus 3 Pascal seconds, and a Pascal is just a Newton per meter squared. So in terms of this, okay? So, convection we talked about. And this is what we refer to as free convection, both in the mantle for the first part and then in water. You could also look at forced convection. I guess I didn't talk about it here. And that would be a heat flux, which would be by, for instance, having flow driven by a pressure gradient. And so this would give you what we've defined as Q of water. So from Darcy's law, we could write that Q water is equal to minus K over mu dP dx. So if we know the permeability, viscosity, and the pressure gradient, we can get this. If we multiply this by the cross-sectional area of this, then the volumetric flow rate is equal to QW times area. And then if I get rid of this, then forced convection would be, heat thermal would be equal to fluid flow of water times specific heat capacity times its temperature. So this would be degrees centigrade. This would be specific heat capacity. So this is joules per kilogram degrees centigrade. And this would be, well, this would work out to be what? In terms of units, this would be a velocity. This would be meters per second. Right. And it has to be that because where's Darcy's law? Because this is units of meters squared, pascals over Pascal seconds over meters, pascals, meters squared. So this is a velocity, meters per second. So meters per second, joules, and if we work out those, this would be meters a second times joules per kilogram degrees centigrade times degrees centigrade. And so from that, we'd lose centigrade, we'd lose, which is we'd lose kilograms, and we'd lose meters, and this become meters squared. And so the units would end up being in terms of joules per meter squared per second. So that's the heat flux. So the amount of energy that's coming out of here is measured in joules, and it's coming out per unit area, which is meters squared, and it's coming out per second. So this ends up being power. So we'll talk about that later on in the class, but that's useful to talk about. All right, so we know something about the distribution of these components. So we've talked about magnitudes of heat fluxes. This is for a different continent. Iceland's here. Greenland is up here somewhere off to the northwest. And the distribution of heat flux is there. Not surprisingly, high heat flux is in Iceland because we have the Mid-Atlantic rift pulling it in part. And so there's high heat flux all the way along that, including down in the part that's below the ocean. If you look at Europe, we mentioned on this map that these individual yellow stars are geothermal plants. And this perhaps is Salts, which is on the border between Germany and France. And if you look here, right here, this is exactly where it is here. So this is a border between Germany and France. This is the River Rhine, comes up here and flows ultimately. The Netherlands is basically the Rhine Delta. So this Rhine Rift Valley is in a rift valley, the Rhine Rift Valley. And that's exactly what we talked about last time, that if you pull apart the crust, then as you pull it apart, it will break. And as a result of that, you get these horst blocks dropping down. And in areas of extension, this is the River Rhine that goes into the page that's sitting in the bottom of this valley. These faults happen to be useful areas, useful conduits for fluids to be traveling in. So even though this is in the central part of a continent, there's not very much heat flow, but you could perhaps, and this is what they have done, you could drill a well from the surface into the zone that is present within the fault, and this fault area has higher permeability than the stuff around it, and so you can inject cold water, have it go across the reservoir, and recover the heated reservoir as it comes out here. So this has to be also in an area of slightly higher heat flux, this darker color that we have here. The other two in Europe, those other three yellow stars, these are both in Turkey. Don't know much about them. Lajarello was the very first geothermal field in the world. Maybe in the 1910s or 1920s or 30s, it existed here. The second one was in, this is a liquid-dominated reservoir, liquid water, and the second one was in New Zealand, which was a steam-dominated reservoir. Different techniques used. So those all rely on temperature. So how can we use what we know about now to be able to say something about the things that we've maybe taken for granted? We made this point when we were talking about the reserves of geothermal energy. The hydrothermal reserve, I think in the US, was something of the order of 10 to the 4 exajoules. The budget for the US in terms of fossil fuels is something like 100 exajoules, and so this is 10,000 exajoules comes from hydrothermal in terms of the reserve. Apparently the EGS reserves are 10 to the 7 exajoules. And so we could calculate that. And so we could do that by looking at the size of the continental US, roughly a few thousand miles across and 1,500 miles north to south. If you do that in terms of kilometers, it's about 5,000 by 2,000 kilometers. We can calculate the total energy would be equal to the volume multiplied by the density of the rock that holds the heat times its specific heat capacity times the temperature. In the same way that we calculated advective fluxes, this advective flux was the density and heat capacity multiplied by the temperature that's held in there. So this would be the temperature that's held upstream. This packet of heat is carried downstream at this velocity, and so the rate at which this comes out physically as water is this velocity multiplied by its cross-sectional area. So rho Ct is the amount of thermal energy, and the volume of that block of rock which isn't moving is the amount of total energy which is included in it. So this part multiplied by the volume, in our particular case here, is exactly this expression we have here. So this is the advecting amount of fluid, and this was its volume that it has, volume per unit time as it comes out of the end of the cylindrical core. So if we take this, then the volume is given by 5 kilometers by 2,000 by 5,000 kilometers. If we look at the estimates for this, if we do it between 4 kilometers and 10 kilometers, so this distance here is 6 kilometers. So if we want to calculate what this volume is, then the volume is going to be is equal to 2 times 5 times 10 to the 6, 5,000 by 2,000 times 6. So that is going to be equal to 60 times 10 to the 6. This is wrong. This should be 6, right? And so this is not 10 kilometers, but 10 to the 6 kilometers. I realized this was the previous set of notes. I corrected in another set, but I didn't include those in your packet. So this is the volume in terms of kilometers. The density of rock is of the order of 2,500 kilograms per cubic meter. The specific heat capacity for rock, not for water, because this is the heat that's locked up in the crust between these depths, is of the order of 1,000 joules per kilogram per degree Kelvin. And the temperature difference, if we go down from 4 kilometers, if it's at 25 degrees centigrade, then 4 kilometers is 100 degrees centigrade. 10 kilometers by 25 degrees centigrade per kilometer is 250. Difference between those is 150. Kelvin or degrees centigrade, it doesn't matter. I've used 100 just because to make it simpler. And if you do the math, this should be 10 to the 6. I think that's right, times 1.5. So this should actually be 10 to the 24, which would be 10 to the 6. So it comes out at roughly 1.5 times 10 to the 6 exajoules. And so the estimate that we used was 1 times 10 to the 7. It's off by maybe a small amount, but it's just maybe different constraints. So that's exactly where it comes from. It's a very simple thing to be able to calculate. Just taking a volume, taking how much energy is locked in that volume, being the product of density, specific heat capacity, and temperature. This is saying that what we're going to do is we're going to change the initial temperature of this region. Yeah, no, it's not the difference between these. It's wrong. It's the average of these. So it would be 100 plus 250 divided by 2. So that's about 350, so it's 175. So if you're able to reduce so the average temperature of this would be this. So this is 100, this is 250, halfway between it, the average between those is this. So this is the temperature that you're taking from 175 maybe down to 0. So if we wanted to be strictly correct in doing this, this would be 175 degrees centigrade, or Kelvin, say. This is just the change. So that would change this estimate by a factor of 2. This would be 3 instead of 1.5. And so that's the easy way to get that number. So that's where it comes from. And so that's, I guess it comes out of this graph here. This here is the magnitude here. So this would actually, it's spot on. This is 14 times 10 to the 6 exajoules. So this is the estimate from this report. The future of geothermal energy is now 20 years old. It was commissioned by DOE to try and make the case for EGS by taking a rational look and looking at the key problems in developing EGS. And so this is the estimate that came from that. So this would be 1.4 times 10 to the 7 exajoules, which is this estimate. And that's actually pretty close to what we got, right? Although this would change to 3 if we use the correct number. And that's all that's been done. If you want to get a more accurate result, you could also take it and divide this height that we have here. I'm not trying to make you go crazy by scrolling through this. If you wanted to, you could also, I don't think you'd get a different result. If you had, for instance, the temperature changing with elevation being something that was like this, then all that you do would be you divide it into individual portions. Just use Simpson's rule, right? And do it discretely rather than as a continuous function. But that's all we did. So what we did was we chose a line. We took the midpoint on that line, said that roughly the change in this point is the same as the change in this, and so by moving this line to get to this line here, then it just ends up being this total area under the curve. You could get it a variety of different ways. So that gives us our estimate for that magnitude. So that's where it comes from. That's what they did simply. And yeah. So that's all we'll talk about today. So I guess we've tried to make the point. One, worldwide, the distribution of heat flow from the subsurface is concentrated at plate boundaries, where we might like to put our plants because the heat flow is largest. Interior to continents, the heat flow is much less, but there's still a significant amount of energy locked up in the crust if we can get access to it. Because of the plate boundaries, the heat is relatively high within the section, and the heat flow rate is very large. Then that represents the low-hanging fruit in terms of the most economically advantageous location to exploit, because you have lower drilling depths and you know that you can actually circulate water fluid to be able to recover it. And now all of the areas which have relatively high heat flow have been tapped to be able to tap the hydrothermal resource. So that is maxed out, just like most dams on the surface within the US for hydroelectric power that can be built have been built, and so there's no more capacity in US rivers. There's no more capacity in terms of the hydrothermal resource. If you want to exploit geothermal energy, you have to go for the non-conventional resource, which would be deep geothermal energy, EGS, and that resource is staggering. Instead of being 10 to the 4 exajoules, it's something like 10 to the 7 exajoules. But the problem is that we have to get at it. The challenge to us in getting at it is, one, we know everywhere we go in the crust we're going to find hot rock. It's going to be slightly deeper in places where the geothermal gradient is shallower, and so we have to drill further, but as long as we get to that depth, we're guaranteed that we'll always have heat. What we don't have everywhere in the crust is the ability to be able to remove that volume of rock to the surface. The only way we can do it is by using a geological heat exchanger, and that heat exchanger that we use is by forced convection. Not free convection, these convection cells, but by forced convection, where we take the portion of that thermal energy that's present within the crust, its high temperature, its specific heat capacity, and the density of the rocks in which it exists. So this would be 2,500 kilograms per cubic meter. But to get it out, we have to use a heat transfer agent, which is water. We circulate water. By circulating water, the water that is circulated goes through from the injection well to the recovery well. It comes out at an effective volumetric flow rate, which is just a velocity multiplied by the cross-sectional area of this tube. And so this now becomes the flow rate of water, which represents the ability to be able to convect by forced convection water out of the system, and convect with that water, heat being piggybacked on top of it. So this is the mechanism by which we need to do that. So we need to have a place where we can get high flow rates in the crust. And that's why hydrothermal areas work so well, because they're broken up by deformation that occurs here. But as you go into central parts of the crust, that doesn't exist, and so you need to be able to make permeability, and usually that's done by hydraulically fracturing, either in shear or not. And so that's why I don't understand quite, as I said, maybe on the first time I guess it was last Tuesday, I don't quite understand how well this works. And so I won't turn the sound on, but you'll get the idea. You've seen it already with the sound. I think it wasn't recorded because it wasn't working before. And so EVOR, it's for a company that uses geothermal recovery by conduction, not by convection. So their whole mechanism is to drill down to where the heat is. So you have to drill down to 3 kilometers if you want to get temperatures of the order of 100 degrees centigrade. And they're going to show you that. And then once they get down to that depth, they build themselves a geological heat exchanger. And so that has water advecting through it, but not through the rocks. It's going just through the borehole. So they build these boreholes, which are steel casing. They get them to link up by using their patented IP, intellectual property or technology. And then they set up this geological heat exchanger. And so the idea is that it doesn't recover fluids from the subsurface, nor does it pump any fluids into the rock, but it pumps those fluids into the pipes. And so if you look here, this is the arrangement they get. They're quite far apart. They're 5 kilometers apart on the surface. They inject blue cold water into it, or a heat transfer fluid. That gets heated up as it goes across the circuit, and as it gets to the other side, it's hot, it's less dense, and so it will rise buoyantly. So they make the case that if you have a heat transfer liquid which changes density a lot, such as CO2, then it will change its buoyant force a lot, and it will want to rise, and you don't have to expend any energy actually pumping, because the so-called heat pipe effect means that it will drive itself naturally. Their other innovation on this is to take away the between boreholes link on the surface and have 2 boreholes going down, and link the tops of those 2 boreholes together so that you have a continuous circuit that's going through this, which is quite clever as well. I can't see this. So maybe I'll stop it. And so now the blue fluid is the cold fluid going into it. It goes across this multi-pronged radiator only through the steel wellbore, and then it comes up the other side as hot water. You take the heat out of it by flashing it to steam and generating electricity. You cool it in a condenser, and then you re-inject the same water as cold water on the other side. It goes across the reservoir in a different circuit, and then comes up the other side hot. It heats up as it goes across, so this is much less dense than it is on this side, and therefore it drives itself. So that circuit could survive without any so-called parasitic losses. You don't have to provide a pump in that particular case. But the problem with this is that if you think about the behavior within this, is that you have, this is your circuit, goes down, it goes across, and then it comes up to the surface. So if you look at any particular component here, if you draw a cross section across here between A and A prime, then you just have a well. And if you want to get heat to that well, then you could think about the well as being a system like this, a slice of the cake. This is T1 and this is T0 temperature. And so you could think about unwinding this. So you have a block that looks like this. It happens that it would be slightly tapered, right? But let's not worry about that. So this is T1, this is T0. And so if you look at the temperature change as you go along here, and this is X. And Fourier's law says that the heat flux out of that system is equal to the thermal conduction multiplied by dt dx. dt dx or dt dr is given, and so it's controlled by conduction only. And so if this conduction is a very small number, which it is, we think for rock it's 1,000 watts per meter degrees centigrade, we can calculate the amount of heat flow we'd get into this. And because it's a very small number for this thermal conductivity compared to driving heat flow across, where basically advective flux would say that you're taking this block of rock and you're physically transporting it to this end in a given amount of time. That's what physically convection is. You're not really moving the rock, but you're transferring the heat in the rock into water, and then that water is moving into the wellbore. We're not doing that in this case. We're driving it only by conduction. And you can do the calculations, and it ends up being a very small number compared to what you'd expect. So I don't quite understand how their patented technology really works, because it's intrinsically limited by conduction into this. The only way you can make this a big number would be by taking that cross section, and instead of it being a circular turn, you could put a whole bunch of these close to each other, and I guess to have them so in other words, the cross section that you'd have here, instead of having a single pipe, they already have multiple ones, right? They probably had half a dozen, but you could fill it up with lots of pipes. And so these individually would only get a small amount of conduction to themselves, but if you sum all of them, then all of a sudden it becomes a large number, because instead of just one of these, you have 10 or 100. So that's the only way that you can make that system work, because intrinsically the rate at which you can gather heat to this pipe is controlled by conduction, not by convection as in other subsurface geothermal systems. Okay. All right, so I will stop there. So next time we'll talk about what happens to fluids in the subsurface as they change temperature. Sometimes they stay as single fluids, sometimes they change phase, and so we need to understand a little bit about thermodynamics. Actually, we'll go through heat conduction, convection briefly again before we talk about phase changes in these systems. And we'll spend the third week, I guess, doing that. So that's all I've got for you today. So we may have finished a bit slightly early. Questions?